Right, this is a video on movement detection or change detection. Um, I've got a number of points I'd like to quickly run through, and they are as follows. The purpose of the presentation, how does it differ from more traditional methods? Um, what can movement detection be useful for? What is needed to detect movement? What can it not do, this method that I am introducing? And the broad guidelines around how much it would cost, and the way it's run. So you can see some things on screen. This is part of a demonstration, and I will very quickly run through these bullet points and then go into this presentation. I will make it as succinct as possible, and hopefully you can stop and rewind if there's anything you don't understand, or get in touch with me directly. So the purpose of this presentation is to advertise that JLS, Jersey Laser Scanning, has the capability and the equipment. Excuse me. How does it differ from more traditional methods? Well, the traditional methods that people have used to detect whether something is moving are the Mark 1 eyeball. Um, Sometimes it's quite obvious. You're looking at cracks and things like that, potentially using a ruler or a tape measure or a laser tape measure. These are all perfectly viable methods. It depends on the critical nature of the movement that you're trying to detect. Um, Total station. So these are, I'm sure 90% of the audience here are aware what a total station is. However, if not, they're the big boxes sat on big yellow tripods. When you drive past roadworks and people have that big box and someone else is standing with a reflector further down the road and they're measuring points. That total station has a laser in it and can turn and zap specific points, and tell you where they are relative to it. And you can monitor a number of individual points. And that is, in fact, how much of movement detection is done nowadays. Um, Sometimes it's through GPS coordinates, which the total station knows where it is and therefore what it's targeting, and then can give the coordinates of that specific individual point. So, how does the new method differ? Well, it uses point clouds rather than individual points. It uses the 3D laser scanner, which spins around at 360,000 measurements a second with panoramic photography and things like that, and effectively paints the area with a number of points, just like the total station, getting an individual point. But those points, when there's effectively more than one of them, um, but in this case, what I'm going to demonstrate you is each point cloud has about 21 million points. It is referred to as a cloud of points, or colloquially, a point cloud. Um, that can be created by a 3D laser scanner, and is in this case, but can also be generated by a drone through photogrammetry, or by a camera specifically through photogrammetry. But the techniques needed should be tied down and very accurate. Uh, so what's the difference between um, the old methods and this method that I'm introducing today? Well, other than the total station and the ruler and the mark on eyeball looking at specific points, um, for example, someone on this scan would want to monitor various points on a wall down here. So they do one here, one on the corner, one there, one there, one there, and they monitor those individual points. Um, Everything else in between is effectively ignored. But in theory, if those individual points are moving, then the total station, the ruler, and so on will be able to identify that, and that may lead you on to what is moving and why, and further investigation. With point clouds change detection, it's measuring 21 million points. And it's doing it with relative accuracy. So the relative distance between here and here is combined within the system. And if you do a second scan over here of the same area with some changes in it, and I'll go into that in more depth in a second, um, it is trying to tie that relative accuracy of this building versus this wall versus this bank and so on all together again. And then you compare this one with this one, and you can see where any movement has occurred. And a heat map can be created, so it can highlight anything greater than 1 centimeter, 2 centimeters, or whatever scale you want. But I'm going to demonstrate that here. So that will bring you onto the area that has changed, which you may not be targeting specifically, but any bulges or changes or emissions or cavities that weren't there in scan 1, which is this one on the left, and scan 2 will be highlighted, and also other areas. So if you're doing a slope, for example, it may not just be the crack in the wall that's changing. It may be a bulge in the earth or a movement in the slope in another area. And those two combined, even if you weren't looking at it, it'll draw your attention to it. So that's the snapshot. What's it useful for? What can movement detection be useful for was one of the markers that I had. Monitoring a wall with cracks or bulges, monitoring a slope or a flat surface to see what is changing and where, because it'll draw your eye to it rather than marking a specific point and monitoring that point. Um, Monitoring a large object relative to its surroundings. An example might be subsidence, or a tree moving its roots underground because of a different things going on underneath the ground, which isn't creating obvious bulges, but the tree is moving relative to its surroundings. So it will pick that up. Um, uh, Less dramatic consequences than a tree falling over or a large object or a slope sliding down could be that a fence has moved after a storm, um, or basically anything that may have changed. Um, However, what is needed for movement detection? You need a minimum of 2 scans. You need one before and one afterwards, or scan 1, scan 2. And you can have scan 3, 4, 5, 6, 7, 8, 9, 10, essentially all being compared to the original scan, or being compared between each other at some points to identify the vectors of movement and what's going on holistically. We also have access to an international team who we've been very lucky that their background is in Canadian mine pits, and they have some serious understanding of what's going on underneath the surface um, of areas and how it may affect what's going on above and how solid things are. So, what is needed to detect movement? 2 or more scans at different times, so you can compare them. Um, you need the equipment that can generate a point cloud, and that would be 3D laser scanner, uh, very accurate differential GPS, so survey grade GPS, um, and or photogrammetry, a point cloud derived from photogrammetry. Plenty of videos on the internet about what photogrammetry is, but essentially lots of photographs moving um, around a static set of objects, and the individual photographs can triangulate each individual point, and the process is exactly the same, generating a point cloud, albeit via a different method than 3D laser scanning. What can it not do? What can 3D laser scanning or point cloud change detection not do? Well, I've had experience of this, and this is a wall collapsing whilst monitoring, and there was no indication of movement up to that point. We were monitoring individual cracks, um, and after discussing this with someone else, saying as much as I could identify, there was no movement up to that point, and the subject matter expert said, well, that's known as a brittle failure. And the context was there was a month's worth of rain overnight, the night before a wall collapsed. And that was the cause of it. There was no indication other than perhaps during the course of that evening of rain. However, um, I don't think anything can detect brittle failure because it's catastrophic and instant with no warning. So, how much does it cost? Um, it will depend completely on the area being monitored and to what degree, and how difficult it is to scan or create a point cloud on that area. Um, I suspect because there's not huge amounts going on beneath the surface, it's more about software and capability, that it's going to be cheaper than you expect. So on with the presentation. Sorry for that preamble, but it was important. So what did I do to use a demonstration? I'm going to keep these two windows open, and show you what was collected. So here is a, oops, Daisy. Here is a point cloud. This is the scan point. It is an area. And what I have done is put out something obvious here, which was a tub of tufts of grass, uh, and made sure there was some foliage behind me. I wanted to demonstrate the vegetation penetration capabilities of LiDAR, which is an active laser beam that goes in between the blades of grass and so on, and can pick up the surface underneath, um, to a greater or lesser degree, but much more accurately than uh, otherwise might be visible from above. So if I double click in here, and by the way, this is the sort of information that one would receive from me with change detection. So we have a panoramic photography, so we can look around and see what was there effectively with a Mark 1 eyeball, and see the situation. So that's scan 1, scan 0. Can't do anything with that. It's a base or a foundation scan, and it's going to be used to compare stuff to. So I'm just going to go back to that view. We're going to have a look at scan 2. In fact, I'm going to bring this one here so you have a general overview. That's just the point cloud. It's a bunch of dots. If I zoom right in, you can see the individual dots, and they're colorized by the photography. So scan 2, at another time, literally, I think about 30 minutes later. Um, this isn't georeferenced. This is purely relative accuracy. So if you look at these coordinate system down here, it's a randomly generated user coordinate system, but it can be georeferenced, therefore giving you specific Jersey grid coordinates. So what's the difference in this scan? Well, I wanted to test the capability. So um, if you see on the left-hand side here, this one, you've got one square there. So I put another of these tiles. These are extruded polystyrene tiles I use for ground control for drones to identify specific points on the ground. They are 25 millimeters in depth, so thick. I can't remember how they are across, but they're 25 millimeters thick in depth. So on here, there was one. On here, I put a second one, so one there and the original one underneath. I also scooped some of the tufts of grass out, to try and demonstrate, how accurate this process could be. Um, as far as the rest of the ground's concerned, there was nothing there, but I put down a couple of small things on the ground there and there. I put down a single tile there, and I think just a single tile there, and wanted to see if this process would identify and pick things up. So what's next? Using a program called Cloud Compare. These are the two original scans. So that's scan 1. So I've imported this into Cloud Compare. Then we have scan 2. So we've got all of this in Cloud Compare. And the process is this point cloud is going to be registered to this point cloud. So they're going to be brought together, and mathematically, statistically, it's going to uh, give me an indication of how similar the 2 point clouds are and bring them together so they are as close as possible, so overlaid on top of one another. What that will do is then allow this second point cloud to be asked the question, how far is the nearest point in this point cloud compared to the point cloud that you are sat now very closely to? That information about how far away that point is from the other scans points is then colorized, and it's given a what's known as a scalar field, an extra bit of information in the point cloud per point, and that is used to colorize the point cloud. And this is the example. So this is the second scan only, and it's been colorized by how far away it is from this point cloud after bringing them as tightly together as possible. Um, and then the colorization here on the right hand side, the scale bar, is showing that out to 20 centimeters is where I initially wanted to start. Anything that is 0 means that that point is within 0 millimeters through to, um, let's have a quick look at the colorization here. So 25 mils or 2.5 centimeters is where I had it fully red. Everything else in between goes from blue, no movement, to green, which is somewhere in the region of 1.25 centimeters or 12.5 millimeters, and then um, 2.5 centimeters would be red, and anything beyond or greater than 2.5 centimeters is also red. And these scales can be absolutely adjusted to interrogate things further. However, what we're seeing here is that all of the blue, and for my purposes, the the light or the darker green that is associated to the blue, excuse me, is showing that very little movement has taken place in the two areas, and that's verification that the 2 point clouds are coming together appropriately. But other than that, there are areas of red. So why they're red? It's because there are distances involved, and that brings your eye immediately onto it. And the difference between that and measuring a crack or a ruler is that you're focused on the specific thing that you're trying to measure. So if there was a target here, it would pick up no movement because there is no movement between these two scans, and over here and so on. But if it did it in this area, it would identify that there are greater things at play and other things happening. So um, let me go to here. And what else can we do with this? Other than bringing your eye onto it, it will allow us to look at things in more detail. So yes, we know that there is red there and red here. And so we can go to our second scan. And if it was geo-referenced, we could identify a specific coordinate and then go and look at that. But here it's relatively simple. We've got the garage, we've got the curb, and we're looking for this area in here. And if we were to go into here, we would see that something is going on there. And because it's in 3 dimensions, albeit coming from this direction, we can get a pretty good gauge of something there. So if we double click into the photography, and this is only uh, HD photography, so 1080p, it's not 4K or anything, but you can see that between the two, it would bring your eye, if you weren't expecting any movement, that down here would bring your eye onto an area to look into, and you could gauge what's going on. On a slope, it's just as important because it may not be restricted to one area that you're monitoring. It could be above or below, and there could be other telltale signs which could help with fixing the issue or making sure that it's shored up somehow. What else can this do? Um, well, essentially, it can do sections and profiles and cuts all the way through. So what I'd like to do is show you an example. So this is that same point cloud um, seen from above. I am going to make it orthographic. So the perspective is removed and we're looking directly down. Um, Now, these areas of red and these red areas down here, that's mostly because this was black and shiny and plastic and moving. So it was moving, hence it's got bits of red. But black is a very bad reflector of light, so laser light, sunlight, etc. So black and shiny objects are going to get a poor return, but the things around it should be, by contrast, very accurate. So let's have a look at these section cuts that I wanted to demonstrate. Um, I'm going to turn the entire large point cloud off, and I'm going to look at a specific section cut through this point, which you can see highlighted if I toggle on and off, and it's going through this red patch here. So I turn off the large point cloud. That section is being looked at from above, so I'm going to come at it from the side. So we are now looking at it from this direction through a section cut sort of through here like that. And what you're seeing, oops, are the 2 point clouds. This is scan one, colorized by the photography. And if I toggle this one on and off, this is the new one, which has been colorized by distance from the previous point cloud. So that's why this information here is showing up in a different color, um, there to there. Um, and all of the other bits are blue because they haven't moved relative to the first scan. Let's have a quick look at the top one. So what other section cuts have we got? There's one there, and there's one on the grass tub. So we will have a quick look at that. So the original had that much grass in the top in that specific, I think it's 5 centimeter depth section cut, and that's how much was removed. One could do a volumetric analysis on that very easily. So you could find out how much has moved and try and figure out where it's gone, which may be a useful part of the process. So looking at other ones, and I'm not going to go back and forth as much this time. I'm just going to show you where the section cuts are. So there's one through that. We've got one through the small red marker there, which I wanted to investigate. One through that tile, one through that small marker, red marker, and one through that tile. So let's look at those. So this is the whole point cloud. This is the log or lump of something which I had there. And as you can see, there's a rainbow effect because at the very bottom, it's still between 0 and 1 centimeter, so it's blue. Then it rainbows up into a point further away from something that was the closest point before, and then red at the very top because it goes beyond 2.5 centimeters. And like I said, you can adjust those parameters so things jump out more quickly. This one is the second tile, and as you can see, that tile shows up as being different from the ground, and that's what the original looked like. That's what it looks like after the movement has been detected, or the movement was there. And this shows the absence of movement as well, obviously, because if things go away, the absolute distance has changed to a negative degree. And if things are added or there are bulges, then it is an absolute distance away from the original point that was measured, and therefore will show up red as well. So that was that second point. This is showing that that log is there. And finally, we are looking at that last tile there, and we can perform measurements on there or interrogate things further. So hopefully that gives some indication of how this works. In the case of a single scan with a 3D laser scanner, it can do a slope, it can penetrate foliage, and things like that. And I suspect that it may help shore up things before they get to a point where they have to be completely replaced. However, that's for the subject matter experts. I'm purely the measuring guy, but I can help with identifying movement. So I hope that's of use. Any questions, please don't hesitate to get in touch. Thank you. Bye-bye.